forces. So calculate the spring constant for a spring that extends 200 millimeters when a 2.94 Newton weight is hung on it. Oh my gosh, I can't draw today. So what do we know? 200 millimeters, that is a distance. What is that in SI units? 200 millimeters would be 0.2 meters. And we are given 2.94 newtons of a weight. Now, is that a mass? No, right? Newtons is the unit for a force. So it is the weight force. So the scenario is we have a spring, and on the end, you might have done this in class, you have a certain amount of mass on the end, which actually pulls down the spring with a certain weight force, such that it will extend, in this case, 0.2 meters. So quite a long spring. And we are looking for the spring constant, which we denote by K. Looking at our formula sheet, we know that Hooke's law is F equals negative K times X, where F is the force, either the restoring force of the spring, or in this case it is the force we are applying to the spring, and X is the distance it is extended or compressed. And the negative just tells us that as you pull a spring, the force that the spring is providing is going to go against you, right? It's going to want to pull back in if you pull it out. But we can rearrange for K, the spring constant, as F divided by X. And you'll notice I've dropped the negative sign here. And again, that's because the negative sign just tells us the direction of the force the spring is providing relative to how we are pulling. But here we are given the force acting on the spring. I guess short moral of the story, spring constant is positive regardless. And so that's 2.94 newtons divided by 0.2 meters, which gives us 14.7 newtons per meter. Right? Force divided by distance, newtons per meter. Alright, and that is an achieved question. Question B. We have a block, wonderful, attached to two identical springs and hung from the ceiling. Just by inspection, it looks like, the springs are the same length, and it looks like the distance of the connection points are equal. So let's assume that. On the diagram, add labeled arrows. Labeled meaning we give the name, or like a shorthand, to show the forces acting on the block. Cool. So the block, it doesn't say it, but let's assume it has some mass, right? Otherwise, it wouldn't exist. And anything with mass has a weight force, which we can denote as either capital W or weight, or even mg, right? Mass times gravity, or F capital G. Any of these are fine. For me, I'll just leave it at weight. What other forces are involved? If this was the only force, it would be accelerating downwards, right? But since it's hung, that sort of implies that it's like hanging there, like stationary. So we will need forces acting upwards. Do we have any support forces? Kind of. So these two lines are the springs, and where they're connected onto the block, that would actually be technically a support force because they're in contact. But more generally, we would describe this as a tension force, as the spring is like under tension due to the block. However, we could simply label that F1 and F2, right? Or even capital T for tension 1, capital T for tension 2. So either of those conventions is fine. And the size of the arrows, roughly the vertical component of the tensions should add together to equal the weight force, right, if it's balanced. But that can be quite rough. You would be wrong if your tension forces were like this and your weight force was just like that. That's clearly accelerating upwards, so make sure they're a bit closer in size than that. Okay, what next? So now draw a labeled vector diagram to show how these forces are acting on the block, how they add together. So in vector addition, we add vectors by connecting the tail of one vector to the head of another vector, and we do that for all of the vectors. So let's start with weight. That's our weight force. So to the head, let me just color code this. So this will be T2 will be green, T1 will be red. So to the weight force, we will add T1, something like that, and to T1, we will add T2. And you'll see that in my diagram, it is a closed triangle, and that tells me that the net force acting on the block is actually 0. So just to summarize this question, in part 1, we drew a free body diagram and we showed the weight force. We then also showed the two tension forces, and we could label them as like F1, F2 or T1, T2, provided by the springs. And we made sure that the tension forces were a little bit smaller than the weight because they would add together to give the weight force. And then in our vector diagram, I started drawing mine with the weight force because it was the largest arrow, and then to that I connected the tail of T1 to the head of weight, so that's at this point right here, and then from the head of T1 I connected the tail of T2, and I finally connected the head of T2 to the tail of weight, and we have a closed vector diagram indicating the net force is 0. And overall, getting both of those correct would be merit. And either or would be achieved. Okay, moving on. This athlete, very buff, he's holding a uniform rod, as you do, 2 meters long, and it's in the horizontal position. The mass of the rod is 3 kgs. Calculate the forces Fa and Fb that are required to hold it in equilibrium. So this is an equilibrium problem. Who would have thought? And that involves calculating torques and net forces. So firstly, I don't know if you've ever held like a broom or something long like this as this guy is holding it, but it feels quite heavy. And that's because its center of mass that's probably too long. Let's just draw this relative to the other arrows. Its center of mass is, probably near the center, right? Since it's uniform, in fact this one is exactly in the center, and it has a mass of 3 kgs, so it has a weight force of 3 times 9.8, which is, what's that, 30 minus 0.6, 29.4 newtons. So that is the weight force of the rod. So to do the analysis, the two conditions that we need to meet are that the net torque is 0 and that the net forces, or the net force rather, is 0 as well. So to calculate the torque, we need to first pick a pivot point. So it could either be his hand at A or B. I think the mark scheme chose A, so I'll choose B just to be different. It works for either. So B is our pivot point. So I'll say pivot point B. And about that pivot point, we can calculate the torques. So we'd calculate the torque from his hand at A and the torque from the weight of the rod at that position. So let's do that. And this is using condition 1, so that FA times the distance it is from the pivot point, which is 30 centimeters, so that's 0.3 meters. Force times distance gives us the torque. We know that the net torque is 0, so this torque must be equal and opposite direction to the torque generated by the weight of the rod. Okay, well, let me explain that one more time. Take two. Let's work out the anti-clockwise torques first. And so the only force that's going to want to rotate the rod this way is FA. So anti-clockwise torque is FA times 0.3. In other words, 0.3 FA. Just as nice algebraic notation. Secondly, we will calculate the clockwise torques about point B, and the only force that is wanting to turn or rotate the rod clockwise is the weight force, right, of the rod. So torques clockwise is that weight force, 29.4 newtons, times the distance from the pivot point. So I chose B, so this distance here is 1 meter minus 30 centimeters, so that's 0.7 meters. And so that's 29.4 times 0.7, 20.58 Newton meters, right? Force times distance. And using condition 1, we know that the net torque must equal 0. So I'll just write it out in full. Anti-clockwise torque must equal clockwise torque. So 0.3 FA must equal 20.58 Newton meters. Solving for FA, divide both sides by 0.3. Divide by 0.3, 68.6 newtons. So that is FA. And FA is acting downwards, right, as per the diagram. So FA, tick. Now FB, we could work out if we made A the pivot point and did all those calculations again, or we could use the second condition, that the net force must equal 0. In other words, the forces acting up, FB, must equal the forces acting down, FA, plus the weight force. So we go F up is FB. Great, that's easy. F down is FA plus the weight, which is 68.6 plus 29.4, which is, what's that? Oh my gosh, I can't remember, 30, 98? Yeah, 98. And we know that the net force is 0, so the upwards force must equal the downwards force. In other words, FB must equal 98 newtons. For it to be in static equilibrium. And getting both of those would be a merit. If this question instead asked, for example, state the conditions required for equilibrium, and we did this first part, this whole question would have actually been an excellence. So best practice just to write the conditions, because it will help you with your analysis anyway. All right. Oh yes, the classic jelly on a spinning plate problem. Yep. Classic. So, circular motion, it is spinning, the plate is spinning rather, and the jelly is on top of it, and the jelly remains on top of it at this position until eventually it slides off. And we need to name any relevant forces, talk about velocity, and describe the path after it slides off. So just a reminder, circular motion, for an object to be in circular motion, it must have a net force inwards, and we call that a centripetal force. Right, it's not a force itself, it's just a net force, so Fc, which results in a centripetal acceleration, AC, also acting towards the center, while its velocity at any given moment is tangential to its path, or perpendicular to AC or FC. Right, but in a moment, the acceleration causes its velocity's direction to change. Right, it's accelerating inwards. Yeah, like so. So its magnitude isn't necessarily changing, its velocity, but its direction is changing, which still requires an acceleration, which comes from a net force, which in this case comes from friction. Right, so it's the friction the jelly experiences on the plate that is keeping it in this circular path, circular motion. So let's try put that together in a few bullet points. In these types of questions, you don't need to write an essay, right? Make sure our physics is accurate, and I personally like bullet pointing. So let's start with that centripetal force. So centripetal force is required for the jelly to undergo circular motion. And why is that the case? And where does this force come from? Right? This comes from the friction between the jelly and the plate. That is providing the centripetal force. So this net force, right, or centripetal force, same thing, provides acceleration, centripetal acceleration, centripetal acceleration, and that is acting inwards, causing the velocity of the jelly to continually change directions and maintain the circular motion. So far we've commented on the fact that we need a centripetal force, right, for circular motion, that it comes from friction, that this force actually results in an acceleration, which is what is changing the velocity, keeping it in circular motion. Okay, and now we haven't commented on either of these two bullet points. So if I'm being critical of my own response, I've probably gone on a bit too hard on this first one. So let's try simplify it. Let's do that now. So I see all this hard work. I'm going to delete it. Look at that, it's all gone. And let's try that concisely. So we could say the friction between the jelly and the plate is providing a centripetal force hence acceleration inward, causing the circular motion. So pretty much exactly what I had before, but much more concise. So friction is the force. It is linked to the centripetal force, like the net force, resulting in an acceleration, causing that circular motion. Now, second part of the question, how does increasing the velocity affect the situation? So in our data book, or our formula sheet, we know centripetal force is mv squared over r. So if we increase the velocity for the same radius and same mass, it would increase the centripetal force required. And again, that comes from friction. So if we keep on increasing the speed, we will need more and more friction to maintain that motion. And there'll be a point where we don't have enough friction, right? And then it'll slide off. So in words, we could say as speed increases, the frictional force required, or the centripetal force if you want, required to maintain its motion also increases. And finally describing its motion after its first slides off. Back to our diagram, if we removed FC and AC, its velocity is tangential to the circular path, and its motion would actually follow that tangential path, right, until it's decelerated due to like the friction of the floor, or it hits a wall or something. So we'd say the jelly slides off and follows its tangential velocity. And that would be excellent. So let's just quickly recap this one. It is a circular motion problem, and we are asked to explain or link a few concepts together. Firstly, we had to talk about the forces, and we acknowledge the only force, assuming the plate's not curved up, the only force is friction that's preventing the jelly from slipping off. We then discussed how if we increase the velocity by the centripetal force equation, we know that the frictional force required also increases, and then there'll be a point where it slips off and it will follow its tangential path due to its momentum, right, because of its velocity. And that is it. Excellence for everyone. See ya next time.